Determination of DRH from IUH. 6.6. Describe briefly the procedure of preparing a DR unit hydrograph for a catchment. Effective rainfall should be uniformly distributed over the basin. If there are 5 rain gauges in the basin, which represent the real distribution of rainfall over the basin, all the 5 rain gauges should record for almost same amount of rainfall during specified time. A watershed shown on the right here fully marks this stipulation, while converse is true in respect of left one. 6.7. Explain the procedure of using a unit hydrograph to develop the flood hydrograph due to a storm in the catchment. Unit hydrographs are used to estimate flood hydrographs by multiplying each ordinate of unit hydrograph by the volume of runoff. The hydrograph theory is based on the principle of opportunity such that discharge varies directly with runoff depth. 6.8. Describe the S-curve method of developing 12-hour UH by using 4 hours UH of catchment. Solution. In this case, D equals given duration equals 4 hour and T equals required duration equals 12 hour. Step 1. Draw 2 columns next to given UH. Column 3 and column 4. These 2 columns are filled consequently as follows. Initially mark dash in first row, rows up to preceding interval of DR of third column. In this case, D equals 4 hour, those marked dash up to T equals 0 only. Step 2.1. Now make addition column 2 and column 3 and write in column 4. Step 2.2. Then write the result at the next row in column 3 as shown by arrow. Step 2.3. Again make addition column 2 and column 3 and write it in column 4. Step 2.4. Then again write that result at the next row in column 3 as shown by arrow. For example, at time 8 hour, drag last ordinate from column 4 in column 3, 20 as shown by arrow. Now do addition of 80 plus 20 equals 100 and write in column 4. Continue this operation till the end of column 3 and column 4. Step 3. In column 4, we get S-curve ordinates which are nothing but the running summation of flow. Now, log this S-curve ordinates by TR as shown in column 5. In this case, T equals 12 hour. Note, always be log your S-curve ordinate by the duration for which you are going to derive UH. For example, if you are going to plot 8 hour UH from given 24 hour UH, then in step 3 log your S-curve ordinates by 8 hour and vice versa. Step 4. Now deduct that logged common from S-curve ordinates. Column 4 minus column 5 equals column 6. This is necessary because we have as sum value which should be converted into single flow value. This will give us DRH of T over D cm ER. In this case, T over D equals 12 over 4 equals 3 cm ER. Thus, column 6 is DRH of T over D equals 12 over 4 equals 3 cm ER. Step 5. This is the last step in which we divided last column by ratio of T over D. In this case, T over D equals 12 over 4 equals 3 cm for getting required of our UH. 6.9. Explain a procedure of deriving a synthetic unit hydrograph for a catchment by using Sanders method. Among several known methods for development of synthetic unit hydrograph, the one suggested by F. Sander 1938 is most commonly used. Sander analyzed a large number of hydrographs from drainage basins in the Appalachian Mountain region in the United States, ranging in area from 25 square kilometer to 25,000 square kilometer. To sketch a unit hydrograph, it is necessary to know the time of peak, the peak flow, and the time base. The elements must be determined for every particular or regional location of the drainage basin. Sender proposed the following empirical formula for the lag time hour. From midpoint of effective rainfall duration, T sub r to peak of a unit hydrograph, T sub p equals T sub t times L sub c raised to the power of 0.3, in which T sub p equals the basin lag in hours from midpoint of effective rainfall duration, T sub r to peak of a unit graph, L equals the length of the main stream from the outlet to divided in kilometer per second, L sub c the distance from the outlet to a point on the stream nearest to the center of the basin, and sub t equals a coefficient. The location of the center of area may be determined by cutting the basin outlet from cardboard and making the point of intersection of plumb lines drawn with the map suspended from different corners. The coefficients C sub t varies from 1.0 to 2.2, with lower values associated with basins of steeper slopes. For the standard duration of effective rainfall, T sub r, sender purpose, T sub r equals T sub p over 5.5. For the range of this duration, he found that synthetic unit hydrograph PQ sub p in COMEX may be obtained from the equation Q sub p equals C sub p over T sub p times A. And in COMEX per squared kilometer by the relation Q sub p equals C sub p over T sub p, where A equals the drainage area in square kilometer per second. C sub p equals coefficient ranging from 0.4 to 5.0. Q sub p equals peak flood in cubic. For the time base T, in days of the synthetic unit hydrograph, U.S. Army Corps of Engineers adopted the following expression: T equals 3 plus 3 times T sub p over 24. These equations are sufficient to construct a synthetic unit hydrograph for a storm of duration T sub r. The value of sender's coefficients C sub t and C sub p are found to vary considerably depending upon the topography, geology, and climate. Sender indicates that the coefficient C sub t is affected by basin slope S. Lensley, Kohler, and Paul House have suggested the expression for T sub p in which the basin slope S has been considered. T sub p equals T sub t times LL sub C over square root of S times N, where N equals 0.38 and C equals 1.2 for mountainous drainage areas, 0.72 for foothills, and 0.35 for valley areas. 6.10 What is an IUH? What are its characteristics? A two-parameter variable instantaneous unit hydrograph, or IUH model, is obtained from the generalized Muskingum model by the S-hydrograph method. The ordinate of the variable IUH vary directly and the time elements inversely, with the intensity of effective rainfall raised to a power between 0 and 1. The method of differential correction is used to obtain estimates of the model parameters from complex storm events. 6.11 Explain procedure of deriving a DR unit hydrograph from the IUH of the catchment. For finding the unit hydrograph from IUH, the area under the IUH is plotted with respect to time at the point. The entire area from the start of IUH at different time interval gives points of S-curve. If a unit hydrograph of TR duration is required, the S-curve so arrived at is shifted by TR and difference in the ordinates of the two S-curves is computed and divided by T. The resulting curve forms the unit hydrograph of TR duration. To illustrate the derivation of UH by Nash method, an example is presented. Example, a storm of mild intensity was experienced in the catchment of river by Baitarani during the form 26.9.75 to 28.9.75. The rainfall was rather non-uniform. The average hourly rainfall over the catchment and the resulting observation discharge at Anandpur site are furnished in table 1 and 2. The area of catchment of river Baitarani up to Anandpur is 8,570 square kilometer. With this set of data pertaining to the storm, an IUH followed by the unit hydrograph of 1 hour unit duration have been computed below. The various steps involved in the procedure are as follows. 1. Separation base flow from to find DRH. The anticipated recession curve of the smaller peak just before this flood was continued till the time of the peak. Point B. A suitable point was chosen to the failing lamp at a distance of about 2t to 2.5 t, where t is the time from the rise of flood hydrograph to the peak. This point B and C were joined by the straight line. The curve thus separates the base flow from total flood. The base flow thus separated is deducted from the corresponding ordinates of the flood hydrograph to get the direct runoff hydrograph or DRH. Number 2. Separation of rainfall excess from total rainfall. The total hourly rainfall average over the basin is shown in the table above. Since the storm under consideration is the month of September and there was a heavy storm in August and yet another storm of small intensity in early September, the loss may be considered to take place at uniform rate. Let the loss be at the uniform rate of x mm per hour. Additionally, the total volume of DRH is worked out to be volume of DRH equals 3,344 comics times 3 hours, where 3,344 is total sum of DRH ordinates and 3 hours is time interval between two adjacent DRH ordinates. Total direct runoff equals 13,032 times 3.6 over 8,570 equals 5.475 mm, where 8,570 is the area of catchment of river Baitarani up to Anandpur in squared kilometer. Now let the loss rate x be more than 2 mm per hour, equating 14.61 minus 3x equals 5.475. We get x equals 3.045 mm. Substituting the value of x, the effective rainfall at different time is obtained. For the purpose of analysis, the hourly ordinate will involve a lot of computational work, and therefore only the 3-hour rainfall ordinates have been considered. The hourly rainfalls are assumed to be uniform during 3 hours, and accordingly, the ordinates of the DRH and ERH are shown in table A.1 below. Table A Point 1. And ordinates of ERH. Number 3. Calculation of N and key. MERHI equals first moment arm of ERH equals first moment arm of ERH about 0 over area of ERH equals 1.3x 3x times 3 over 2 plus 0.525x 3x times 3 plus 3 over 2 over 3.3x 3 plus 0.525 3x equals 5.85 plus 7.088 over 3.9 plus 1.575 equals 12.938 over 5.475 equals 2.363. MERH2 equals second arm of moment equals second moment of arm about 0 over area of ERH equals 1.3x 3x times 3 over 2 squared plus 0.525 3x equals times 3 plus 3 over 2 squared over 5.475 equals 8.775 plus 31.894 over 5.475 equals 7.428. MDRHI equals first moment arm of DRH equals first moment arm of DRH about 0 over area of DRH. So mao ni diyang solusyon and equals 2.6 268740 over 13,032 equals 20.622. MDRH2 equals second moment arm of DRH. Second moment arm of DRH about 0 over area of DRH. Mao na diyang solusyon. Now and K equals MDRHI minus MERHI equals 20.622 minus 2.363 equals 18.259 and N times N plus 1 times key squared equals MDRH 2 equal minus MERH2 minus 2 N key MERHI equals 501.651 minus 7.528 minus 2 times 18.259 times 2.363 equals 407.931. From the above two equation we get K equals 4.038 R and N equals 4.471. Hence, for analysis, the value of K and N may be taken as 4R and 4 respectively. In case of very sandy soil characteristic of catchment, N may be taken as 5 if its value works out to be 4.47, whereas for hilly or semi-hilly regions of catchment, N should be 4. 4. To estimate the ordinates of IUH, once N and K are found out, the ordinates of IUH can be found very easily by using the relation U times T equals 1 over K times N minus 1 times T over K raised to the power of N minus 1 times A to the power of negative T over K. This will give ordinates in units of seconds to the power of negative 1. To find the ordinates in comic, it is multiplied by catchment area contribution due to 1 mm effective rainfall. Thus, for first time unit, U times 1. Area equals 8,570 times 10 to the power of 6 m squared. K equals 4 times 60 times 60 seconds times N minus 1 equals 4 minus 1 equals 6t equals 1 hour. Note that in term t over k would be 4 hour as we considering in t in hour. This step is repeated for rest of time or units generates IUH. The ordinates of IUH are given in table below. It will be seen that the last ordinate is never zero. This is because of the fact that the recession of IUH is generally defined by an exponential function which has zero value only at infinity. Hence, the recession is terminated at a suitable point and volume adjusted. Number 5. Derivation of 1 hour duration unit hydrograph from IUH. The t to the power of th are ordinates of the 1 hour duration unit hydrograph can be very easily found by the simply taking the average of t to the power of t hour and t minus 1 to the power of th are ordinates of the IUH. Column 2 the table above gives the ordinates of the IUH rounded off figures. The column 5 gives the ordinates of the 1 hour duration unit hydrograph. 6.12 distinguish between A. Hydrograph and hydrograph, B. DH, UH, and IUH. A. Number 1. Hydrograph is graphically plot of discharge of a natural system for river versus time. A hydrograph is a plot of intensity of rainfall against the time interval. It is usually represented by a bar chart. 2. Hydrograph shows variation of discharge with the time at particular point of a stream. It also shows the time distribution of total runoff at the point of measurement. The area under hydrograph gives the total rainfall occurred in that period. B. Unit hydrograph is a direct run of hydrograph resulting from 1 unit, 1 inch or 1 cm of constant intensity uniform rainfall occurring over the entire watershed. The concept of unit hydrograph is based on linear systems theory and followed the principles of superposition and proportionality. The instantaneous unit hydrograph or IUH of watershed is the result of one instantaneous unit of rainfall exists distributed uniformly over the watershed. Problem number 1. Obtain a unit hydrograph for a basin of 282.6 km squared of area using the rainfall and stream flow data tabulated below. In this process, use the horizontal straight line method to separate base flow. Empirical unit hydrograph derivation. Separate the base flow from the observed stream flow hydrograph in order to obtain the direct runoff hydrograph or DRH. The stream flow at the start of the rising length of the hydrograph minus 150 meter cube per second. Base flow minus 150 meter cube per second. Number 2, compute the volume of direct runoff. This volume must be equal to the volume of effective rainfall, hydrograph or ERH. So this is the formula. Thus, for this example, VDRH equals 200 plus 650 plus 1050 plus 750 plus 600 plus 400 plus 200 plus 75 times meter cube per second times 300,600 seconds equals 14,130,000 meter cube. Number 3. Express the VDR in equivalent units of depth. VDRH in equivalent unit of depth equals VDRH over a basin equals 14,130,000 meter cube times 282,600,000 meters squared equals 0.05 m equals 5 cm. 4. Obtain a unit hydrograph by normalizing the DRH. Normalizing implies dividing the ordinates of the DRH by the VDRH and equivalent units of depth. So, mao ni si dyan table. Number 5. Determine the duration of the ERH associated with the U obtained in 4. In order to do this, A. Determine the volume of losses. V losses, which is equal to the difference between the volume of gross rainfall, BGRH, and the volume of the direct runoff hydrograph, BDRH. V losses equals BGRH minus BDRH equals 0.25 plus 2.75 plus 2.75 plus 0.25 cm per hour. 1 hour minus 1 cm equals 1 cm. B. Compute the F index equal to the ratio of the volume losses to the rainfall duration, TR. Thus, F minus index equals B losses over TR equals 1 cm over 4 hour equals 0.25 cm per hour. C. Determine the ARH by subtracting the infiltration F minus index from the GRH. Thus, T equals 2 hours. Unit hydrograph obtained above is a 2-hour unit hydrograph using the principle of superposition and proportionality encoded in the discrete convolution equation. So this is the formula. Qn minus nth ordinates of the DRH. PM minus volume of the MTH rainfall pulse expressed in units of equivalent depth. UN minus M plus 1 is the times UN minus M plus 1 TH ordinates of the UH expressed in units of meter cube per second per cm.